Hello everyone, I'm Paolo Casale from Hermos Munich, and today I'm going to tell you about some recent work that we did for rare variant association testing, specifically introducing a Bayesian framework that can integrate multiple variant annotations during an association test. So while in GWAS, we typically focus on common variants. Rare variant association studies look at the other side of the spectrum. And in this talk, when I talk about rare variants, I refer to variants within an allele frequency that is lower than 0.1%. So if these variants do have an effect, these effects tend to be stronger than common variants. So their rare variant association studies yield results that are more interpretable. But the challenge is that rare variants come in much larger numbers than common variants, and most of them appear in very few samples. And in practice, the rarer you go, the more you have. So while in GWAS, we focus on, we can do single variant association testing. For example, using a simple regression approach. In rare variants, this is not really possible because of the low statistical power that we have due to the rarity of these variants. Most of them only occur in a single individual in the whole biobank, even in large biobanks with hundreds of thousands of samples, or in few individuals. And so, the test has a very low, if not zero, power. So what people have done, and this is just one approach to rare variant association testing, is to collapse multiple rare variants in a single gene-level genotype, so to say. So these typically these are called burden tests. And for this type of test, people tend to focus on damaging coding variants for a given gene. And then you can collapse them into a gene-level burden score, as I was telling you before, using a very simple aggregation strategy. For example, you can just count for each individual how many damaging rare variants they carry. And then again, you can use a simple regression model, as before, but now to test for association between a gene-level burden score and the phenotype rather than a single variant.
Just to make sure I understand. So when you're saying damaging variants, you mean loss of function or any other kinds of? Thank you.
So what counts as damaging variants? Yeah. So one definition, as you're exactly saying, is putative loss of function. And you can call them using standard variance effect predictor tools. And these are variants that have a strong impact on the protein. These include stop gain variants, for example, which truncate the protein, or frame shift indels and disruption of the splice site that change heavily the amino acid sequence and the protein products. You may also define damaging specific missense that have very high pathogenicity scores, such as SIFT and polyphen2. This can, you can easily annotate your variants again using VEP with these scores that build on principles of conservation like SIFT, or polyphen using a supervised model on labeled variants to produce these scores. That's a bit of a detail I will not get too much into, but the main idea is that you can annotate your variants with existing tools and get pathogenicity scores. Let's say more recent way in which you can define damaging variants, which is using machine learning sequence-based models. And so there's many of them. Here I'm making one example with Splice AI. This is a model that was trained to predict splicing from the genetic sequence. And what you can do after you train the model, you can give the reference genome, and you get a wild type score. And then you can give the same sequence, but you make a single nucleotide substitution, and you get a mutant score. And then by computing the absolute of the difference between these two, you can have a measure of the impact that substitution has on splicing. This is called in silico mutagenesis, and high delta score identify damaging variants according to this type of definition. Spliceado is only one example. We've seen there's many. And Haki also talked a bit about this yesterday, focusing on the informer. But beyond Spliceado, I know we have done the last 10 years many. We have DeepC, for example, which can predict genomic tracks from sequence. We have Primate AI that's trained on principles of conservation. Primate AI 3D, the TADS protein structure. DeepRipe that can predict RNA binding protein target preferences. More ESM1B that's trained on imputing amino acids in a masking problem. Alpha missense, the informer, and most recent Borzoi. So many have come out, many more will come out, and so the questions, right? I mean, how we combine these effectively if we want to do a rare variant association test. Also, we do need a flexible framework for doing that because we expect more and more models to come out in the next years. So what people have done to integrate this course is at the meta-analysis level. So you can compute different burden scores for different annotations, then get a p-value, and then use Cauchy aggregation of p-value to merge these tests into a unique one. And so this is an example where you perform a test for putative loss of function, damaging missense, and other non-synonymous variants, and then merge these three into a single test. And of course, you can use the same type of strategy looking at a larger number of annotations, where you also consider these in silico mutagenesis scores from models such as Splice AI or Primate AI. However, why do we meta-analyze in the first place, right? All these tests are performed on the same population level data. And specifically, a unified and flexible population level model should have more power of detecting rare variant tests, rare variant associations. And so that's what we do in this work. So we propose a Bayesian framework for doing that. We call Bayes-Arvat. So we start from rare genetic coding variants within a gene and a bunch of annotations that we have on them. And these are all different pathogenicity scores and other genomic information that we have on the variants. There is a full list there you can read, but at the high level, we have 3 consequence scores. One, we include the allele frequency. We have 5 functional scores, 2 that capture splicing, 5 regulatory annotations, and 8 that describe RNA protein binding. Then, of course, you can use an approach where you aggregate them in the gene level burden score and then test association with the phenotype. But in this aggregation, we want to do this in a flexible way, so we introduce aggregation parameters phi that define how these variants are aggregated based on the annotation. It's a function of the annotation. And since data is really sparse, we need to be Bayesian. So we set a prior on the aggregation parameters phi, and now we can infer a posterior distribution for each gene trait pair. So this is the high-level framework. So the model is simple. So it's just a Gaussian model on the trait where we have additive effect from covariates such as sex, age, and genetic principal components, and then we have an effect from the gene level burden. And this is the likelihood. So a bit about the function first. We use a sigmoid additive function, right? Where we are linear in the variance and in the annotations. And the sigmoid here models the fact that once the function of a gene is broken, further annotations do not disrupt the gene more, right? So you have sort of these saturation effects. Then you can think about this product XA as producing annotation-specific burdens. This is number of individuals by number of annotations. and these phi are the weights that each annotation has in the aggregation. And then the bit zero, so we shift this within the sigmoid. We set it to make sure that individuals that carry no variant, they are assigned a burden score of 0. And then, of course, a bit on the annotation preprocessing. These to work, we normalize them, such as higher value correspond to more damaging mutation. We use the Fred scale to weight annotations based on their genome-wide rarity, and then we scale these all between 0 and 1. So now the question, how do we set the prior, though? So in principle, this prior should capture our expected impact of these annotations. So for the probability loss of function, we set this prior here, which I think is best interpreted after we squash them through our sigmoid function. So this corresponds to having a prior that individuals that carry one probability loss of function, they have a burden score very close to 1. And then we give, of course, a lower impact to other annotations like missense and non-synonymous, and we give quite low impact to all the continuous annotation coming from these deep learning models and other machine learning based models, because these are many, and some of them are not always reliable in all cases. And so basically, by setting this type of priors, we are really heavily relying on a putative loss of function test, but then giving the opportunity to the model on a gene trait based trait pair to reweight some of the annotation and contribute to the burden.
Sorry, how should we interpret the negative phi? Could you remind me at least how phi is used in your burden? Sorry.
Yes, so phi is just is the linear model, but is within the sigmoid. Yeah.
So if it's negative, it's reducing the...
Yes, yeah, but you have this saturation effect. So anyway, also on this side, so it doesn't, this is log scale here, right? So if you look at how, so this violin plot shows the prior basically on individuals that carry a single one of these different mutations. And so you can see the actual, prior that we put on these annotations. So they're never negative, right? This is log scale. But in the latent space, you can have a downshift. Yeah.
But why is it at 0? There's nothing less than 0. Like, what was that choice, or is that just an example?
No. We wanted basically all the continuous annotation. We wanted them to only have positive impacts on top of consequences, right? Because this is basically categorical, right? It's either one of these three, right? It's either peel-off or missense or other non-synonymous, right? So this is categorical, and this can only add on top of that. Great, so that's our model. This is basically defines our likelihood. Then I also told you about the prior. Now, how do we do inference? Right? How do we compute the posterior? So this is not tractable due to the sigmoid and some other constraint that we have on the priors. And so we resort to variational inference. We introduce an approximate variational posterior just using mean field. And then we optimize a lower bound. So this black box variational inference is actually being covered maybe by Rajesh, who actually authored this paper in the other room at the same time. But here I will just say to understand what we do in practice. By maximizing the elbow, we estimate both the model parameters theta here and the variational parameters. So we also infer an approximate posterior distribution. Great, but ultimately with this model, we want to do association testing. So we want to compare the model H1, where we have we model the effect from the burden, and versus a model where we have no effect from the gene burden. We, of course, if we were able to compute the log marginal likelihood of the alternative model, then we could just compute a likelihood ratio test and perform this type of test. But in practice, we cannot do that because this is intractable. And so what we do, we replace the log marginal likelihood alternative model with something with a lower bound. We do not actually use the evidence lower bound. It's a bit technical. I think it's nice parenthesis. We use a tighter estimator so a tighter bound for this. And this is the importance weighted elbow, which is computed via importance sampling using the variational posterior that we learned, maximizing the elbow. Yeah, and then basically by doing this, we have now an approximate likelihood ratio test that since we have a lower bound, right, the test statistics is lower, higher p-values, and so overall this test tends to be conservative. We of course want to test though calibration, despite the theory tells us this is conservative, and also power and simulated data. So for that, we use the real genotypes from UK Biobank, considering 100,000 are related individuals. And then, under not genetic effects, we can confirm calibration. Here, each point is a gene, right? So it's a gene level test. And then we also perform power analysis where we use real data annotations, again using the same 25 annotations that I briefly presented before. Yeah, and so what we see, so we compare Bayesian with a Cauchy aggregation that puts together, does a single test for each of these 25 annotations, then aggregate using Cauchy. Cauchy that only integrates consequences tests and a standard putative loss of function test. And as you can see, if we consider a simple ground truth model where we only have effects from peel-off and missense, then simple model perform as well as this Bayesian framework. But as you increase the number of contributing annotations to the burden, then their power drops, and Bayesian is the only one that maintains statistical power. We also apply this in real data, so we analyzed 12 blood traits in the UK Biobank in 300,000 individuals approximately. And yeah, overall, you can see the traits. Here is the number of discovery after accounting for multiple hypothesis testing. And as you can see, we find Bayesian finds most association for most traits. Cumulatively, this looks even the difference is even more evident. Great. One question that we get a lot is how important is the prior? And I mean, we made these choices, and we decided to put a lot of weight into peel-off and then down weight to all others. How about we consider, a flatter prior where peel-off, missense, and non-synonymous, we put the same weight on them. And we see that this really makes a big difference, right? So if a peel-off dominant prior gives a much larger number of discovery. Interesting though, even if Bayesian is very similar to a peel-off test due to a strong mass on the peel-off, we still can identify many associations that are missed completely by putative loss of function test. And I want to take one example to show what actually happens, right? So this is a gene trait pair for which a putative loss of function test gives a very high p-value, but we get a very low p-value from Bayesian. And so we looked into these and other examples in detail. And here I'm showing the distribution of the mean of the posterior of the burden from Bayesian. This is its values versus the percentiles. And each point here is an individual. And yeah, I'm coloring in red individuals who carry a loss of function. Now, what a loss of function test does, it assigns a 1 to all individuals in red, right, and 0 to all others. Well, he said, with Bayesian, we upweight the burden for many individuals who do not carry a loss of function, and we have some individuals that even if they don't carry a loss of function, they have as high of a score as individuals who do, right? So we also can use something very similar to SHAP values to visualize which are the important annotations, which annotation are playing a role here. In this example, we see that missense playing a very important role. We see strong contribution from DeepRipe and DeepC. This is gene trait specific, right? So depending on the gene trait that you analyze, you can go back and look at which annotations contribute the most. So of course, it's not all necessarily beautiful. We also miss some associations if we compare with a Cauchy aggregation of the annotation. So then we looked at these cases specifically and think, okay, why do we miss them? And so to have, so here I'm showing malus of 10 p-value. You can see the Bayesian VAT basically misses them, and you have a very, we have strong signal instead from the other method, the Cauchy aggregation method. And so to get an intuition why this happened, we looked at single annotation tests, and basically it's pretty evident and maybe obvious as well that in cases in which the signal is not driven by putative loss of function, we have a strong R priori strongly misspecified, so we miss the association. Just part of the trade-offs that you probably need to accept when considering Bayesian models with priors. Great. I've been talking a lot about burden tests. There's also another framework that is very much used in rare variant association studies. These are variance component models through sequence kernel association test. And here, again, the model is Gaussian. You have a linear additive effects from covariates and all variants in the gene. And on the effect of this variance is modeled as a random effect here, where the variance of the random effect is a function of the allele frequency of the variant, and the Scott authors they choose the hyperparameters A and B of this distribution such that rarer variants have a stronger impact. And then within this framework, you can do a score test, a variance component score test, to assess whether collectively the variants in the gene affect the phenotype. And so what's being showed is that this test can perform much better than burden tests. Typically, the main scenarios in which this has been assessed is when you have relatively high allele frequency definition, allele frequency threshold to define rare variants, and also when only a certain percentage of the variants that you include in the test are simulated to have an effect, so are causal. But in our setting, we see something very different. So when we compare these different burden tests with a simple SCAT test, we see that we use a much lower allele frequency, this 0.1%. And we see much lower discoveries with SCAT test. And even if we use Cauchy aggregation between all the burden and SCAT, we only see a very small power increase on top of the burden. Great. We also support binary traits. So that's it's an extension in which we replace the likelihood, the Gaussian likelihood, with a Bernoulli likelihood, and now we can also do binary traits. Here we analyze 8 common diseases in the UK Biobank. We see very similar results, higher cumulative number of discoveries. We identify all the hits found by other methods +2. And we have lower statistics in general at the genes identified by at least one method. Great, so the preprint result is on bioRxiv. And now, some take-home messages, very high level. So sequence language models using machine learning or maybe deep learning, they open new opportunities for rare variant association studies, because you now have access to these very different ways of defining damaging variants that give you a lot of flexibility. So to actually model these jointly, we developed a flexible Bayesian framework that can integrate multiple annotations. We call it Bayesian VAT. And we show calibration and higher number of discoveries across a bunch of applications. So we are working now, we're cleaning up the software. This will be released with publication. We are extending the framework to model genetic relatedness. So all the analysis that I showed today was on R-related individuals, but now we also want to enable multi-ancestry applications, so that we can analyze the full UK Biobank and also all of us, which is a multi-ancestry cohort as well. And then this idea of integrating annotations to define allelic-series, right? How increased disruption of a gene affect phenotype. We're excited about extending this concept across genes and traits, and potentially enabling interpretable and clinically meaningful insights from these dosage effects. Great. And I'd like to thank Antonio and Luba, students in the group who drove the work, and collaborators, Theo at CGSI and Nakai at ETH Zurich. Thank you very much for your attention.